And our last talk before the break, then, PCC O'Brien, who will be talking to us about characterizing asymmetry in the topography of series, ice, and craters.
All right, thanks everyone for sticking around for one more talk. I'll also be talking about bright stuff in craters, this time on Ceres, which is apparently the most outer solar system object in our potpourri. But that's okay because Ceres is this interesting intermediate case between the icy worlds of the outer solar system and the inner solar system. And the one aspect of Ceres that I'll be focusing on today is the fact that it has permanently shadowed regions near its poles. And these are important because although Ceres is ice rich, its bulk composition is about 30% H2O by volume, and it has abundant ice-related geomorphic features on its surface from pits and brine deposits. In spite of that volatile abundance, Ceres is generally too warm for water ice to be stable on the surface. At its current semi-major axis, ice sublimates relatively quickly under solar heating. The lifetime of a patch of ice on the surface is anywhere from on the order of years to maybe a few tens of kiloyears at most. But there's one place that ice can be stable on the surface, and that is inside these permanently shadowed craters. Ceres has a small axial tilt, which means that topographic depressions like craters near the rotational poles can remain shielded from solar illumination. And in the absence of sunlight, the interiors of these shadowed craters can remain cold enough for water ice to be thermally stable against sublimation indefinitely. And so this makes Ceres appear to be similar to inner solar system bodies like the Moon and Mercury, which also have low obliquities, also have permanently shadowed craters. And for the Moon and Mercury, there are various lines of evidence that water ice is cold trapped in these craters. Similarly, for Ceres, it also appears that there is water ice cold trapped in these PSRs. So the Dawn mission framing camera instrument took images of permanently shadowed craters on Ceres. And although these craters are shadowed, they're not completely dark. Their interiors are illuminated by secondary sources like sunlight that is scattering off of the crater wall. So if you stretch these images, which you can see in the bottom half of this figure, you can peer into the shadow. And when this was done, it was observed then that in roughly a dozen of Ceres permanently shadowed craters, there was bright stuff in the bottom of the crater. And because this bright material is inside the shadow where temperatures are predicted to be cold enough for water ice stability, these bright deposits, which were termed bright crater floor deposits or BCFDs, were inferred to be water ice. And in one case, which you can see in the very bottom right image, the bright material extended just outside the shadow onto the illuminated part of the crater floor, and the VIR instrument was able to spectroscopically confirm the presence of water ice on the surface. So it appears that the permanently shadowed craters on Ceres play a similar role to those on the Moon, on the Moon and Mercury. That is, they are thermally stable sinks for water ice that gets transported to the polar regions, and therefore they're potential climatic records of the body's volatile history. So we know that Ceres is losing water ice through sublimation because of its warm temperatures, but this might be a place where we can probe the evolution of that volatile history. But there are a couple of reasons why Ceres is very different from the Moon and Mercury. The first is that Ceres PSRs are not actually permanent. That's because Ceres undergoes significant obliquity variations. Its axis tilt varies from a few degrees to 20 degrees over relatively short timescales with a period of about 25 kiloyears. So that means that basically every single PSR experiences direct solar illumination for at least part of every obliquity cycle. And so that raises the question of whether the bright material that we see in these permanently shadowed craters, if it's ice, how can it be preserved over heating across multiple obliquity cycles? The second key difference is that unlike the Moon and Mercury, water ice is everywhere on Ceres. So on these rocky inner solar system bodies, any ice that you see in a permanently shadowed crater must have come from somewhere else, either through volcanic outgassing or impact of a comet or water-rich asteroid. But on Ceres, water is everywhere. Even though it's not stable at the very uppermost surface, the crust of Ceres is globally ice-rich. And perhaps the most relevant example of this is that we see that mass wasting and landslides are exposing water ice on the walls of craters and depositing ice-rich material on the crater floor. So Don observed this at two mid-latitude craters, Oxo and Juling. The image on the left here is an image of Juling crater. And we can see on the crater interior these landslide deposits and VIR observations of the crater wall above this landslide show clear water ice absorption features. So we know that ice is playing an active role in shaping the surface, and we know that these mass wasting events are exposing water ice and depositing that ice-rich crustal material onto crater floors. So the bright material that we see in these permanently shadowed craters could simply just be local icy material that is being preserved. And if that's the case, that would be very different from the situation on the moon and Mercury. So the motivation for this work is to assess these permanently shadowed craters, to try and understand what, if anything, these PSRs are preserving and what they can tell us about the history and evolution of water on Ceres. So in particular, some of the unanswered questions that we have are, if this bright material that we see in these polar craters is water, how much water ice is actually being cold trapped at the poles? And how does that compare to supply rates from potential sources, both exo and endogenic? And lastly, in light of Ceres' significant obliquity variations, can we constrain the ages of these deposits? And do they survive across multiple obliquity cycles? Or is the bright material we see today, was that deposited in the very recent geologic past in the last few tens of kiloyears? So as part of this work, we performed the first comprehensive mapping of the morphology of these bright crater floor deposits. And I'm not going to be focusing too much on the mapping because this was done by one of our co-authors. But basically, based on the morphology, we assigned a confidence level that each of these deposits was actually cold-trapped surface water ice. So in the image on the far left, you can see an example of a high confidence case. We have this quasi-circular bright deposit with nice sharp margins. It's contained entirely within the cold, shadowed portion of the crater floor. I think that this is consistent with surface ice. In the middle, we have a medium confidence. There's definitely some bright material in this crater, but it extends outside the shadow, so into places where water ice is not predicted to be stable. And we can see that there's some streaking continuing up under the crater walls, which indicates that there was some mass wasting here. So some or all of this bright material might be ice, but we can't rule out dry mass wasting processes. And lastly, on the right, we have a low confidence case. Maybe there's some bright material towards the top of this crater floor here. But actually, if you look at multiple images of this crater, the location and the extent of that bright material, or in fact, whether that bright material is present at all, varies from image to image, suggesting that in this case, this is an effect of the complex secondary illumination environment in the crater and not actually an intrinsically bright albedo feature. And so the key takeaway of this mapping effort is that of the dozen or so PSR craters that were previously identified as having a bright crater floor deposit, only a handful have morphology that we're really confident in saying is consistent with cold trapped surface volatiles. But for the rest of this talk, I'm going to be focusing on the topography of these PSR craters. Topography that we only have now 7 years after the end of the Dawn mission, thanks to some recent work by Schorghofer et al. They produced shape models of 9 permanently shadowed craters identified as having bright deposits using stereophotoclinometry. Now I'll return to how these shape models were made and some caveats, because the fact that stereophotoclinometry was used to produce shape models of shadowed craters might be raising some alarm bells, but we'll get back to that. But in this work, the authors used these shape models to calculate illumination and temperature within these 9 craters at a range of different series obliquity values. But another thing you can do with this topography is use the shape models to test this hypothesis that significant volumes of water ice are cold trapped at Ceres poles. So we can ask things like, are craters that have bright deposits significantly shallower than the background population of craters on Ceres, as we might expect if there have been significant infilling by ice? And do these craters exhibit any asymmetry in their topography? In particular, asymmetry between the pole-facing slopes and the equator-facing slopes. So as you can see in this animation, the illumination environment and therefore the temperature, the thermal environment, is not uniform in this crater interior. You have a thermal gradient between the equator-facing slopes, which are periodically illuminated, slopes which remain in shadow and therefore remain colder. So because of this thermal gradient, if water ice is present, if it's being delivered to this crater, we might expect that there could be preferential deposition and preservation of ice on the cold pole-facing slopes and preferential removal of ice from the warmer equator-facing slopes, potentially giving rise to some asymmetry in the crater elevations of the interior. So first thing we did was to use these shape models to try and measure the depth of these craters. So we talked about this meeting, we're using this profile method. I've shown 20 profiles here, but we're taking this 3D shape model and we can draw hundreds of profiles to get really good statistics. This top plot is showing these profiles overlaying, and we take a radial average and we get error bars but from the standard deviation of all the profiles. And we use this to measure depth to diameter ratio. So here are the results of that first test showing depth to diameter ratio for the 9 craters that we have shape models for, compared to the global average of simple craters on Ceres, which is the dashed line here. We're dealing with a small sample size, only 9 craters, and it's pretty noisy because of the quality of these shape models and just the fact that Ceres polar regions are very rugged and these craters are pretty heavily degraded and modified since their emplacement. But based on this small sample size, there doesn't seem to be any obvious shallowing of this population of craters compared to the background. In fact, Ceres, like many other bodies, exhibits a trend in depth to diameter ratio, with smaller craters being shallower. And so our results appear to be broadly consistent with that. And we're hesitant to draw any conclusions about the overall shallowing of these polar craters compared to the background population. But that leaves the possibility that there could be some subtle asymmetry between these pole-facing and equator-facing slopes that would suggest that volatiles have played a role in shaping these craters since their formation. So we next tried to characterize that asymmetry, and since we already took all these profiles, we might as well start by using them. And you can see just by looking at these profiles that this crater is not very symmetric. There's a lot of spread from profile to profile. Now on the shape model on the left, I've added this red arrow, which is pointing towards the pole, and I've colored the profiles based on their azimuth, with bright colors being equator-facing slopes and dark colors being pole-facing slopes. And so there are many different ways you could use these profiles to characterize asymmetry, but the first thing we thought to do was to find something that I'm calling here the elevation anomaly of each profile, which is simply the difference between each profile and the average, summed out to some maximum distance and normalized by that distance. The magnitudes of these elevation anomalies is not really important, since here we're looking more for the spatial relationship of these anomalies. The idea being that if a crater is more or less symmetric, then these anomalies should cluster around 0. They should be relatively small, and their spatial orientation, positive and negative, should not exhibit any significant trends. So if we do see any trends spatially with azimuth, that would tell us something. So here is the result of calculating those elevation anomalies for this crater, which is Bilwis crater. And I'm showing this as a rose diagram. Again, the red line is pointing towards the pole. The color of each bar is corresponding to its azimuth. And bars that point outwards are places where the elevation anomaly is positive. That is, the profile plots above the average. And places where the bars point inwards are negative elevation anomalies. And so here we see that there is an asymmetry. The colder pole-facing slopes tend to have systematically higher elevations. They all pretty much plot above the average profile. So here is just summarizing those results for Bilwis, which was one of the craters that had a morphology with its bright deposit that we think is consistent with surface ice. And I've added the maximum temperatures that were calculated by Shorkoffer et al. And so we can see how all of this kind of fits together. In the hemisphere of the crater that is facing the pole, that has colder temperatures, we can see that the profiles look very different in that hemisphere of the crater compared to the brighter colors which come from the equator-facing slopes. And that is confirmed by the elevation anomalies that we calculate, which show this clear asymmetry between the two hemispheres of the crater. And we see the same trend for the other polar craters that we thought had a morphology consistent with exposed surface ice. So here's NP7, shows the same asymmetry, pole versus equator facing, and number 4, which is slightly off, but we still see a clear difference. But interestingly, we also see this trend for the craters that we thought had either no obvious bright deposit or a bright deposit that did not appear to be consistent with surface ice. So here's Damia crater. Did not have a morphology that was consistent with surface ice, but we see the same asymmetry between the pole and equator-facing hemispheres. Similarly with Nkimdu, which is the largest crater that we have a shape model for. And with these largest craters, you can actually see just by looking at the shape model in the upper left that there's a clear difference between the pole-facing and equator-facing hemispheres. It looks like the pole-facing side of the crater has experienced significant slumping. So that suggests that this asymmetry that we're seeing could be consistent with enhanced mass wasting and preservation of icy material in the cold pole-facing hemispheres of these craters. So we do see potentially a systematic trend in these permanently shadowed craters with an asymmetry in the topography where pole-facing slopes tend to have systematically higher elevations, consistent with there being more material deposited on these cold slopes. And the fact that we see this in all of the craters that we have shape models for, not just the ones that have nice, clean, circular, bright deposits, suggests that the presence of bright material on the surface is not necessarily indicative of subsurface composition. And that also tells us that maybe we should look more widely than just the dozen or so craters that, based on images, appeared to have bright material, because this could potentially be more widespread. There are a number of large caveats that have to be attached to this analysis. The first is that just as we've talked about it at this meeting, extracting morphometric parameters like depth and diameter is difficult. And these craters are not nice, fresh, simple bowl-shaped craters. They are heavily degraded, and the polar regions of Ceres are very rugged and heavily cratered. So this is challenging. And there's lots of superimposed topography. You can see in this one what looks like probably a crater formed in the center of this crater. And all of these geologic processes that are not related to volatiles can affect the asymmetry of a crater. So that's definitely something that we have to account for. And another can of worms is that actually identifying the center and the rim of the original crater is very far from trivial. And in particular, misidentifying the center of the crater can really affect the asymmetry that a method like this returns. So we're actively trying to find better ways to determine the center of these craters and ensure that our results are robust to that choice. Another major caveat is the way that these shape models were produced, which was using stereophotoclinometry. These craters, although they are not permanently shadowed in the true sense of the word, parts of these craters are shadowed as long as Ceres is at its current obliquity, which means that they were shadowed throughout the entire Dawn mission, and they were shadowed in every image that Dawn took of these craters. And typically with stereophotoclinometry, shadowed parts of the images are just ignored or assigned null values. But Shorthofer et al. Developed an experimental procedure to try and estimate topography within the shadowed portions of these craters using that secondary illumination. So basically by making these combined mosaics using the raw images in the parts of the crater that are not shadowed, and then stretching the images and using the stretched images inside the shadow, which gets you an estimate of the topography, but this actually violates one of the core principles of stereophotoclinometry, which assumes that illumination is coming in parallel from a fixed location. And that is not the case inside these shadows, because secondary illumination is very complex. And the interior of this crater is being illuminated from many different angles because it's being illuminated by sunlight that is scattering off of this crater wall and thermal emission from these sunlit surfaces. So there's good reason to be skeptical of these shape models, especially in the portions of the crater that are shadowed. But actually, if we just take the shape models and we mask out the shadowed pixels and ignore them, we can see that in many cases, the permanently shadowed portion is actually a small area on the crater floor. And in many cases, we can just visually see the asymmetry, even ignoring those shadowed pixels. So especially if you look at the lower left and lower right, which are the largest craters in the sample, you can see that this asymmetry between poleward and equator-facing slopes extends outside of the permanently shadowed portion of the crater and up onto the wall and rim, suggesting that this is a real effect. So even ignoring the shadows, it looks like there has been slumping and mass wasting on the hemispheres of these craters. So that tells us that what we're seeing is probably a real effect and not, at least not entirely an effect of the stereophotoclinometry method that was used to produce these shape models. So in conclusion, these recently produced shape models seem to reveal an asymmetry between pole-facing and equator-facing hemispheres of these permanently shadowed craters. And we're interpreting this as being consistent with there being mass wasting and preservation of icy material on the cold pole-facing slopes of these craters. And the fact that we see this in all 9 of the craters that we have shape models for suggests that the presence of bright material on the surface is not necessarily telling you anything about whether there are cold-trapped volatiles. And that also tells us that we should go out and look at more craters, because Ceres has hundreds of permanently shadowed craters. And so to really understand what these PSRs are preserving, we need to have more than 9 craters. We need a larger sample size. But that means we need new and better techniques for estimating topography within permanently shadowed craters, and especially with being able to characterize the uncertainty in these crater elevations within shadows. So thank you very much.
Great, thank you. We have about 6 minutes for questions, so I'm happy to. Stuart, go for it.
Stuff that I finally work on more. So I have lots of ideas on finding the center of a crater. Talk to me.
Yeah.
I use 4 or 5 different circle fitting methods, and they all yield slightly different results than what I think an average. Also, the elevation anomaly, that is an interesting thing that I don't think I've seen before. And I have ideas on how to make that better.
Yeah, that was the first thing that popped in my head, and so it was a exploratory, like, let's see what this shows, and it showed something. I don't know that it's definitely not the best thing to use, and it makes it, because it can be positive and negative, it makes it sort of difficult to do statistics about the circularity. So I'm definitely
well. So one of the assumptions is you're dealing with an axisymmetric feature, which it's not.
Yeah.
So just on top of my head, what I was thinking was you have your radial profiles. You could normalize them to between the center and then the highest point and say that that is a unit of 1. You normalize all of your profiles to that, make your average profile. And then you can get a deviation from that. That could, I suspect the results would be very, very similar. But I think that it's more, it would be more accurate.
Yeah.
And it could clean up your signal a little bit. I mean, clearly there are differences, as you just said. The question is perhaps like at the couple percent, maybe even 10% level, could you clean up that signal a little? And I think that normalizing those profiles could help.
Yeah, definitely. Yeah, and if we want to use these profiles to get any sort of quantitative estimate of, you know, how much material is there, then we need to do a better job of normalizing and yeah.
Well, you have my email, so feel free to reach out.
The end of a long day. Anybody at all?
I was just, my only comment while I was listening was the question about how much is the conclusion affected by the choice of the center. So I was really glad that you did in fact confirm that that's going to make a huge difference.
Yeah, and so I tried some, you know, tried to find the point that minimized the residuals on the average profile, but because these craters are so asymmetric, you can get some weird results from that. So I ended up just doing it by eye, you know, circle fitting algorithm, but it definitely could be improved and definitely affects the results.
And since we've discussed depth fitting quite a bit today and yesterday, I'll mention this is another reason why I dislike profiles in general, because it is so sensitive.
Yeah.
Exactly where you put that center point.
Well, if that did not spark any more question ideas, I think that we can break 3 minutes early for break. So let's thank Patrick again.
So we'll break until 15 minutes till the hour, come back for any discussion on anything, be it science, be it methods, be it community, whatever. And if we have nothing, then we can also leave early. But we will reconvene in 12 minutes.